Mhm.
Okay, good morning. Then I think we should start now. And yeah, after a long break, we resume our study and we start from note three, equivalence relations and partitions. And maybe before we dive into note three, maybe we can review what we have done at notes first note and second note. We can just thought about and talk about it loudly. So we have sets,
Mhm.
set operations, and we define numbers as a set, and we also we can just do it like a natural conversation. Also, it means you can talk.
Yeah, I will join in maybe just so far you're enumerating various kind of aspects, and then we can concentrate more or less on some specific
Yeah.
one. Another thing, so basically after we looked at sets and set operations, I think we started
Mhm.
looking at functions and the
Yeah.
related ideas of image, pre-image,
Mhm, mhm,
domain and codomain, and how they can be related, and the properties like
mhm,
injectivity, surjectivity, and bijectivity this way, right?
mhm. So flow, like for me, I remember the general flow was we start from set and
Hmm.
then do the Cartesian product and then we define a function and then I think we did have a look more detailed about the functions and its operations like
Yeah,
yeah yeah
is
yeah
basically we essentially we introduce the concept which is necessary to start with another topic, and that it seems to be a logical way of progressing from sets toward
Mhm,
the definition of details of the function.
mhm, yeah, especially image and inverse image and what happens if we do a if we take intersection or union of function then and its image also yeah injectivity and surjectivity and bijectivity and function composition
Hmm.
so we are like as our chapter or as our like three for like first three notes is about that theory. Yeah, introduction is.
I'm not actually sure. Is this part also related to set theory, the equivalence relations and the partitions?
Mm.
Is that something generally covered in the area of set theory, or is it a separate
Oh yeah, I'm
area?
not sure. I'm not sure.
Mhm.
But in our Kidesu sense, this is part of the basic set theory. And
Before the calculus part or the analysis part starts,
yeah, yeah.
that's the meaning. Yeah.
Mm. And then yeah, as always, maybe we can ask to each other more like drilling sense. I should ask
Hmm.
you what's the definition of function is.
Okay, I'll try to be precise in
Mhm.
the answer. So it's a mapping between elements of two sets,
Mhm.
such that each element in the first set is mapped uh, to an element of the other set, uh, such that such that a single element of the first set cannot be mapped to the different elements of the second set. So it
Mhm.
has to be mapped in this way uniquely.
Mhm.
So it means two different elements of the first set can map to the same element in the second set, but
Mhm.
one element in the first set cannot be mapped to more than one element in the second set.
Mhm. Yeah, I think it makes sense. I mean, also, um, I'm not sure we also need to explicitly state that we should use all elements in first set. for the
Yeah,
mapping.
it's basically something I noticed. I was looking at the lecture by Professor Cho, and basically noticed that he uses the word each, and it
Each,
sounded like, yeah,
like, yeah,
it
so each
sounded like
means,
it's not that important, that it can be maybe ignored. But then I realized it's actually very important, because it means that
yeah,
every single one of the elements in the sort of domain must be mapped.
yeah. Because I also hard to find the like appropriate way to explain the every elements in domain should be used as a mapping, but maybe each is the way to express it like simply.
Yeah, I would say it is the right word, as long as it's not ignored when somebody
Mhm,
listens,
mhm.
right? Mhm.
Yeah. And now you can ask me about, you can request me.
Let's recall idea of surjective, and how it is also, is it a one to one? In another way of saying is one to one.
I think onto was the term of surjective and
Yeah.
surjective.
Mhm.
Okay. So
Surjective is the onto. Injective is the one to one.
yeah, I think it was it. And so surjective function is a function that every image has, no, the surjective function is every element in codomain has at least one pre-image. Yeah, is it right? Yeah, I
I
think.
would say so. Essentially,
Yeah,
the full codomain is covered.
yeah.
So there is no single element in the codomain that is not
Mhm.
covered. And that
So
means the image and the codomain are exactly corresponding.
I think I can also use each element in codomain like we just,
Yes. Yeah, I
yeah,
would say so.
discussed.
Hmm.
Maybe we can ask each other um one more questions to each other, and then we go to equations, equivalence relation and partitions. So easy problem.
Maybe for now we didn't maybe finish in this way. Let's talk now injective.
Mhm.
So one definition we encountered, I think, in our course of study was that there is at least one relation, right? So there has to be no, sorry, at most one connection to the corresponding set, to the second set, right?
Mhm.
So it means either an element in the codomain is unmapped,
Mhm.
or if it is mapped, it's only mapped from a single element in the first set.
Yeah. So for me, I will explain it like at most one pre-image in.
Mhm.
Mhm.
And also, maybe since we are linking the word bijective, which means both of those properties, it means exactly one, right? So then it's like at most one together with at least one. Then
Yeah.
it would mean exactly one.
So for me, I would prefer just like bijective means injective and surjective, but still we
Yeah,
have to
but
finish
basically,
the,
if
yeah,
for example, do
equation.
not rely on the words
Yeah,
injective
exactly.
and surjective, we
Yeah.
can say that every single element in the codomain is mapped,
Mm,
and also mapped uniquely, such that it is only mapped to a single element.
mm. Yeah. Actually, I
Mhm.
was about to ask you to talk about injectivity, but I think you already had it, so maybe you can ask me one question to answer, and then we can go through the equivalence class and partitions.
I think maybe one other aspect we can remember is uh, about inverse functions. So
Mhm.
I think the requirement for an inverse function, the full inverse function, right,
Yeah,
is
yeah.
such that it's bijective.
Yeah.
And then maybe we can say something about like left inverse and right inverse. Maybe it's also like
Mhm.
helpful to give
Yeah,
some consideration.
yeah. So in surjective case, we can have a right inverse function, and in injective case, we can have left inverse function. I mean, I'm not sure it is precise to way that it we can have left inverse function or
Because I think the thing that previously really got me confused was the idea whether it's called left or right. What left with respect to what, or right with respect to what? And then I think we saw that we can see the order of operation that would play a role, and that would decide if it's left or right.
I think we quickly visit the left and right inverse. I think it was around
It was
yeah.
one of the later parts of the topics, and just
Oh,
before function composition, maybe, yeah, somewhere there.
okay, let's think about it together.
Mhm.
So let's start from injective. Is it visible or
Yeah, I can see everything, all the details.
we have left inverse, which means if we have f is injective,
Mm-hmm.
it means we can find g.
Mm-hmm.
So we can make this is identity.
Mm-hmm.
So it means left inverse, right?
Mm-hmm. So basically, function g is applied from the left to function f, right? So
Mm-hmm.
basically, it's means g after f. Yeah. Mm-hmm.
Mm-hmm. This one. Yeah. And the surjective, we have right inverse, and it means if you have A, then we have just like that.
Mm-hmm. Yeah. So
Yeah.
basically, again, here is the right because g is applied from the right, essentially. So first g is applied, then f is applied, and we still get the result correctly. Mm-hmm.
So for me, I think it as of the where they located with respect to composition. So G is on the left,
Mm-hmm.
then left inverse, and G is on the right and right inverse. Maybe we can think about this shortly with
Some
mapping.
examples? Yeah. And also maybe a sub question here would be, can you then say the operation of composition is commutative in case the function is bijective?
So sorry, what I missed you.
Can you say that the operation of composition of functions
Mhm.
is commutative if the function is bijective
Mm,
with respect to the inverse function? Yeah, with respect to the inverse function.
yeah. So I think bijective, then it's commutative.
Yeah, that's how it intuitively feels to me as well. Yeah.
And I mean, I think it's not commutative because the I mean commutative, then the result should be same, but
hmm And
it,
I'm only
even if
saying in
if
case of injective. So
in
first of all,
bijective.
G is the inverse of yeah, bijective. So G is the inverse of F, or F is the inverse of G, and they can be applied from both sides. That would mean the function is bijective, and then it shows that because it can be applied from both sides, that the operation is commutative.
But my argument is these
Mhm.
two functions has different domain and codomain.
But then, for example, in the first case, let's say f maps A to B, then we first map A to B and then B to A. So we return back to A. And
Yeah,
in the
so we
second
have A
case,
to A.
we start with B, we map to A and then back to B.
Mhm. So we
So
have
it
B to
basically
B.
maps B to B.
So
So,
I
so
so I think the structure is preserved, but to be commutative, it should be same, but it's not same, right?
yeah, that's basically so. In terms of logic of operation, it seems like it doesn't matter from which side you apply. It ends up sort of uh, giving you sort of identity in either domain or codomain,
Mhm.
essentially, but in a sense of in which set you will end up, in set A or in set B, it doesn't feel right. Yeah,
But then
but
we can we
maybe it's not quite a valid question here. So maybe we haven't explicitly spoken about commutativity with respect to limitations and restrictions of the
then
meaning.
yeah, then following question is if we set if we make a if we start from like A to A,
Hmm.
it's also A to A, like
Hmm.
using same domain and codomain. And then
Yep.
in this case, it will be commutative.
Mm, uh, uh, I think it can be valid to call that commutative. At least I cannot see why not.
Mm, I want to, maybe we can spend some time to think about the counter examples, or maybe we can really think about some mappings.
Mm,
Mm.
um, one, one,
Maybe it is not a good mapping to find counter example, or
I'm not. I think basically it depends on the meaning of commutativity. So commutativity only refers to the idea that both sides of the operation would work out,
Mhm.
or that they will give exactly the same result.
Mhm.
So, for example, if we have in set A we have 1, 2, and 3, and in set B we have A, B, and C, then basically, yeah,
Yeah.
that would be sort of more
Then
illustrative.
yeah, I also think that in this case it's it's commutative.
Hmm.
Mhm.
So,
Because
so the
yeah,
domain
yeah,
and
okay.
codomain are exactly same sets, and because of that, yeah, essentially they have this clear commutativity, right? So, like,
Yeah, because the reason we failed in the left in this case,
hmm,
because the mapping itself is both was identity, but it was identity about the with the
yeah,
elements
with respect
on
to
the
elements
yeah
of A
A,
and
yeah,
identity with respect to elements of
yeah.
B. Hmm.
But in this case we have same domain, so it will be, let's say,
Like a GX
yeah,
on
yeah,
both sides, essentially,
yeah,
yeah.
yeah.
Hmm.
So it's bijective.
Hmm. Hmm. So it's also nice to give this consideration, right? So even though
Yeah,
it's
yeah,
bijective,
yeah.
it's not necessarily commutative in the sense that it can have two different domain and codomain values. Mhm.
Mhm. But it's so composition was associative for just general setting, right?
Mhm.
I think we had to prove that as exercise in our like first. semester. So I think we can now dive into equivalence relation and partitions. So do you want to
Yep.
discuss more about reviewing stuff, or we can?
I would say basically we have to sort of this was more like accelerating our minds and getting us
Yeah,
to a
yeah.
work state, but we cannot always return to the full set of ideas that we discovered previously,
Mhm.
just for the lack of time.
Mhm.
So maybe in case we encounter some problem that relates to the previous uh, data or the previous information, then we can return. But for now, we just go forward a bit.
Okay. I'll
Hmm.
just bring my water and yeah, just give
Sure.
me yeah, 30 seconds.
Yeah. Oh, probably just quickly grab water as well.
Yeah. Yeah. I mean,
Hmm.
even in World Cup we have hydration break now, so why
Yeah.
not? Yeah.
Yeah. Yeah. That's true.
So yeah, I think we had a brief look, but I think it's good to go through the notes together. Yeah.
Hmm.
So equivalence relation and partitions, and for me, I feel like I'm a bit familiar from this stage. I mean, uh, about how we define equivalence relations, because it does not mean I know this, but I heard of it. But partition, I think yeah, I am still not familiar with how we define the definition, like
Hmm.
just whole definition of partitions. Yeah, let's just go through the notes. So I'll just read following line by line, and then if we want to something to discuss, then we can
Yep.
just hop in. Yeah. So we have recall that F is a subset of a Cartesian product B. So in this case, we are recalling recalling functions that we defined. And yeah, as you said, we have also for each here, for each
Hmm.
X, there exists unique Y. So, I mean, even this sentence is um, sufficient to express all the nature of function. So for each A
Hmm.
means like every element in domain, and there is unique B, and this unique means it should be only one mapping for each yeah.
Mhm. I was thinking about this word unique, maybe, is that if you think in a sense that unique with respect to elements in X, that's not necessarily true. So different elements in X can map to the same element Y. But unique with respect to idea that single element in X cannot map to different elements Y.
Mhm.
Yeah.
Mm. So unique means the yeah.
Yeah, unique with
The
respect to
X.
single element X cannot
Mhm.
map to more than one
Mhm.
element Y. Hmm.
Mhm. So as we discussed, the data type is tuples, set of tuples,
Hmm.
and which is subset of a Cartesian product B. And yeah, satisfying this yeah condition. And we observe that every X has a relation with some elements in B. So in this
Hmm.
case, I think we didn't really um use the relation as a mathematical sense, but more like
I think we
intuitionally. Yeah.
previously we used the word mapping between
Mhm.
elements in one set and the other set,
Mhm.
but we didn't specifically use the word relation.
Mhm.
And so basically, we can say that relation is a more general term than a function is. So function is a specific form of a relation, but there are others.
Yeah. So I think in here it is like introducing relation term, but it is not really in this sentence. It's not relation like in
In
mathematical
here,
sense.
it is an example. Then we have a definition later, right?
Mhm. So I think in here we have an official definition of relation.
Hmm.
So given two sets, relation I always relation R is I always look it always looks like B, but a relation R is a subset of a Cartesian B. Yeah,
Hmm.
like this. And for each tuple in R denotes this notation.
Hmm.
So yeah.
And maybe I can say a tuple with two elements is a pair is a common way to call it instead, right? Because it's only two elements.
Um Sorry, what was
A tuple which only has two elements is a pair. The word for it is pair, a more common way to say it.
pair? You mean pair?
Yeah, yeah,
Yeah, yeah.
because a tuple can have like three
More
elements, 10
general, yeah.
elements. It doesn't matter. Hmm.
Yeah, yeah. So we could like pair like triples
Yep, yep. Hmm.
like so. But why don't
And
we
also,
use the easy way to evaluate?
also maybe one other thing I thought about was here it says given two sets, but can a relation have more than two sets? Is it possible to have a relation with three sets, for example?
Like making triples.
Yeah, yeah. Essentially, a triple would it still be a relation? But I'm just generalizing. Maybe is it or is it not?
So I think strictly speaking, in my opinion, it's no, but I think we can make it because we can like using associativity,
Hmm.
we can do A Cartesian B first,
Hmm.
and then we can do it. So I think we don't have
So
this
basically,
as a
we're saying
relation, but I think we can have
any
this as a
triple can
relation.
be simplified into a pair, and then a next pair after a result of the first one is taken, right? Something like
Mhm,
that.
mhm, mhm. Yeah, because I realized that in so when we construct a function, we also use like function like this. So
Hmm.
it's also like in a tuple sense,
Hmm.
it will have like this format, right?
Yeah, yeah, yeah. It makes sense. I'm just wondering because in a case of functions, essentially a function should have one input and one output. But
Mhm.
this input can be a pair or this input can be a triple. It doesn't matter how many arguments sort of to a function
Mhm.
you give.
And
Whereas, mhm,
even output could be a
yeah, a
tuple.
pair or a tuple. Yep. Hmm.
So I mean in here we are also doing same. I mean, but I think it was actually a good point. Maybe there is also something that we take three sets to Cartesian product,
Hmm.
then subset of it might be something useful.
But
Something.
I'm just thinking. Imagine we're talking about a property of specific object. So let's say one we're talking if the object is round or not. Another one we're talking if it's big or not, and the third one we're talking if it's red in color or not.
Mhm,
And then all those three aspects have to be linked in a relation.
mhm,
So maybe in that case, like we can do it consecutively. So we first check whether it's round and big, and then we check whether it's red also.
mhm,
But essentially, we can relate three different aspects
mhm,
generally, right? The relation between three aspects.
mhm. Yeah. But I think a relation is strictly in this I think we de yeah, we define relation with just two sets, Cartesian product of two sets, because it doesn't not have any problem to even express more, like as we said, like use
Mhm.
first and then using like associativity. So
Maybe it's my general sub question towards the word definition. When we encounter a definition, we can say it is one of the possible ways of defining things, right? So maybe there are alternative ways of defining a relation. But when we're talking about using sets, then we this type of definition can be, for example, unique or maybe not necessarily unique. That's my question, sort of.
you mean this expression
Uh,
of
so, so first, I'm just saying that there can be two definitions which
Mhm.
are equivalent. So
Mhm.
it's a bit funny because we're
Yeah.
talking about equivalence
Yeah,
relation
yeah.
in general. Yeah,
Mhm.
yeah. Mm.
Mhm.
But yeah, I'm just later on we can see specific cases. But for by the way, maybe I'll send you a screenshot. It shows like my phone will overheat and will close the app in 20
Yeah, yeah,
seconds.
yeah. You can just like
I'll
turn
show
it
you.
off.
I'll show you a text because it shows it now. Maybe if you don't mind, I'll switch off the camera.
Yeah, yeah. So
Yeah, I'll just stop the video. But yeah,
uh
I'll later on send you a screenshot. Yeah,
yeah,
because
yeah,
I'm not
yeah,
sure if
yeah.
it's good.
Don't worry. I
I'll send you the
think
screenshot. Hmm.
your question actually has a great point throughout today's topic because we can really check that based on the um today's how we define equivalence relation, and if two I mean even the two expressions are equivalence
Hmm.
relation, then so we are really thinking about what is equivalence and we define in mathematical sense. So I mean after we define what equivalence is, then we can also
Check whether it applies or
check
not in this
whether it
case.
yeah even expression of definitions. Then we
Hmm.
still have problem like circulating problem that of definition of equivalence relation because before we define what the equivalence is. But I think yeah, it's also a good point to think about today's topic.
It can, yeah, sort of give it more dimension to
Yeah.
this
And
additional question.
I think that's the like motivation and the essence why we defining equivalence relations because we want some criteria in mathematics maybe to distinguish what is equivalence and not, and that's the way we are doing this. And
Hmm.
still I'm not familiar with how partition will be plays a role. I mean I
First of all, I think the word partition is mentioned a couple of times in Professor Cho's YouTube video. Then, in case we cannot figure it out just from this material, then we can
yeah,
return to
yeah,
that.
maybe later.
But also, I think once we go through each part here, we will probably come up with a clear definition. Hmm.
Okay, then where were we? Maybe definition of
Yeah,
relation. Yeah,
definition.
yeah.
Hmm.
So we have two sets and it's really general setting. So we have general setting compared to functions. So we have
Hmm.
A Cartesian product B and subset of A Cartesian product B is a relation.
Hmm.
So we had more condition to fulfill a definition of function. That means we need to use every element in domain like first set, and the mapping should be unique, but we don't have any like
Yep. So those
constraints
two
to it.
restrictions are gone essentially. Hmm.
So we can just take subset of generally subset of A Cartesian product B, then it's a relation. I mean, the
I
definition
think
again, yeah.
the only exception would be if it's empty. So I think relation cannot be an empty subset.
Hmm.
But
Why?
I'm um, because when we say relation, it means those elements of A and B are related. And if it's empty, it means they're sort of unrelated, right?
But
But I'm
it
not
also
sure.
gives
It's
us
my
like
guess.
information,
Hmm.
like
It is
unrelated.
information, but I'm not sure whether it would be considered a valid relation. So,
Mhm.
does set this R set R, does it need to have at least one element, or is it also valid if it's empty? So by the strictly looking at this, R is still a subset of A and B if it is empty, but since it doesn't have any elements, so it's essentially sort of says that there is a relation which does not exist between elements of A and B, which is a kind of strange statement in itself, right? But maybe it is a valid one. I'm not sure.
Yeah. So just from the definition, I think that it does not violate the definition of relation.
Hmm.
So empty set is just by the
It
definition
definitely
is a
is a valid
relation.
subset, right? Right. Yeah.
Yeah.
Hmm.
But the question is, it is meaningful or it is just meaningless? I mean, even relation as an empty set is a meaningful or maybe that could be a question.
Hmm.
Maybe
Yep.
maybe we can ask it. So I think if we finish this like chapter 3, we can I think we can have a chance to get some feedbacks for our direction and other stuff
It's because
to process
essentially
information. Oh.
it's essentially the first major topic that we covered, starting with sets and up to the relations. And the next topic is going to be a sort of a new chapter because it's going to be on analysis. So maybe
Mhm.
it's actually a good point at which we can ask Professor Cho some
Yeah.
more nuanced questions.
The empty set as a relation has meaning
Hmm.
in maybe later mathematical sense or not. Maybe
Hmm.
yeah, we can ask this when we had a feedback session.
Yeah.
I think it was also yeah, great point. Yeah, thank you for point out.
Uh,
Okay, so where were we? Now
we
we
essentially finished the definition itself, and now we can look at some examples given.
Mhm.
And then maybe I will also, yeah, once we look at the given examples, but before we go into showing specific properties, maybe sort of before exercises,
Mhm.
maybe I wanted to ask a couple of example questions of some like,
Like
but
this.
no, the questions I had mostly are about the word equivalence relations, not relations in general, but
Mhm.
the equivalent ones. So maybe once we reach that point, then I'll ask some
Yeah,
more
yeah,
questions.
okay.
Hmm.
So I think we are a bit familiar with this, and we use the tuples as this notation. And I think it is more convenient because if we use as a tuple, we use it is a relation as a set R, the set of tuples, like
Hmm.
and the relation between two elements.
Hmm.
But if we use this notation, we don't even make them in a set because this just is equivalent to this. I mean, I
I
feel
would say
like
essentially
I'm
it's
not,
like
yeah,
extracting information about two specific elements.
yeah. But
So if you just write two is tilde r5, maybe
mhm.
it's enough to show that two is related to five, but it doesn't really matter whether our other elements are related to some other number or something like that.
Yeah. So
So you can extract only the piece of information that you
Mhm.
need and ignore some of the rest of it.
Right. It's actually quite powerful notation, and the problem is I feel like I'm not allowed to use a word equivalence yet because we didn't
Because
define it.
here we're talking about relation in general. So for example, a function is a relation, but it is not necessarily an equivalence relation,
Yeah,
right?
yeah.
Mm-hmm.
But I mean, in just like daily life sense, I was trying to say these two notation is equivalence, but we didn't define what the equivalence relation is. So
Yeah,
in
that's
yeah.
so.
So like every function is a relation because function
Mm-hmm.
is a special case of relation that fulfills more criteria. So
Mm-hmm. So it basically has more restrictions essentially because of that. Yeah. Mm-hmm.
so I think we already like even in this last meeting in 6 weeks ago with Tanfia, we discussed about these expressions. So
Mm-hmm.
yeah, reflexivity and transitivity, no, symmetry
Symmetry.
and
Symmetry.
transitivity.
Mm-hmm.
So I one just question is come up with my idea then that like can you think of equivalence relation in real life?
Yeah, that's maybe because it's essentially those three properties are what make a relation into an equivalence relation, right? As long as those three properties are satisfied, then the relation is called an equivalence relation, right? So I'm thinking maybe just to give an example, and maybe to give an example which is more intuitive, is just to consider, let's say, for example, we have in one set, we have different triangles,
Mm-hmm.
and in another set, because when we have an equivalence relation, later it will say like between a Cartesian product A. And when I heard the lecture by the professor, he said it's generally not A cross B, but
Mm-hmm.
A cross A,
Mm-hmm.
but it is still possible to have A cross B. For
Really?
example, yeah,
So
because I was thinking, let's say you have like only small triangles in one set, and in another set you have big triangles, and then you want to say the property by which you want to see if they're equivalent or not is whether they are triangles.
Mhm.
So you still can say in both cases they are triangles, and it doesn't matter. So they're sort of they can be compared to each other with respect to the property that you are trying to check.
Yeah,
But
because
but
we
Mhm.
yeah.
But it depends on what you decide. So let's, for example, say you have only one set, and in this set you have some triangles which are right-angled triangles and some triangles which are not right-angled triangles. So
Mhm.
then you can break them into two groups, essentially, right-angled ones and non-right-angled ones, as one way to compare them and classify them into two separate groups.
Mhm. But that that's like the separation is more like in partition sense, right?
It's both in a partition sense, and basically when you say equivalence, that means you must have the ability to decide whether they, with respect to some property, are equal or not. So, for
So
example, a triangle is equal to another triangle with respect to that it is 3 points connected by three straight line segments. In this
the
way, it is a triangle.
then how can we construct and check the reflectivities, symmetry, and transitivity with that examples like
Yeah,
set.
for example,
Yeah,
let's
yeah.
say we're talking about sets A cross A. So basically, they're both the same sets, and we say if an element A, so a triangle, the first triangle in the set is equivalent to the first triangle in the set. So basically, how do we check this? How do we decide? We just check. Okay, it has three sides. Has all sides are connected and 180 degrees in between the angles that we get. Yeah,
Okay.
so it is.
For a moment, I will just maybe change some settings and we can.
Yep,
I
yep.
write down. Yeah. So we can.
So this notation in where it says the first big Q letter, A tilde RA, we can replace it with A is equivalent to A. because exactly the relation we have here is the equivalence relation. So we can say A is equivalent to A.
Mhm. You mean here?
Yeah. In this case, if we're talking about the objects of our sets are triangles,
Mhm.
and we can say that triangle is equivalent to itself,
I
essentially,
mean,
something like that.
but like, I mean, we have to use just relation, not the equivalence in here
But
because
but but,
we,
but
we
when we say A is equivalent to B, it is a relation, right? So equivalence relation is actually uh, A tilde RA would mean A is equivalent to A, right?
I don't think so because we we just use relation
Hmm.
here. So A relation A
Hmm.
is reflexive, and if A relation B, then B relation A is symmetry. And third, we only use relation, and these three properties of relation is combined. Then we call this
An equivalence relation.
yeah. So we
But
start
I
from
would
just
say
relation, and then
in here first of all I think later there will be an example where we essentially we don't have the second so that we don't have the symmetry and transitivity only because the element is related to itself. So like pairs 1 1, pairs 2 and 2, pairs 3 and 3. So they are both reflexive, transitive, and uh, uh, symmetric
Mhm.
automatically.
But let's get back to the triangle examples.
Yeah, sure.
Mhm.
But we can just actually play it out and see how it works out.
Right.
So A tilde RA would mean tr
So yeah.
triangle.
So my
Mhm.
like first
Mhm.
question is the setting. The set A is a set of triangles.
Yeah, let's, for example, just sort of to simplify, draw a visual triangle inside the set A. So it doesn't matter; it has to be an abstract object, and I think a triangle is a valid geometric object which can be used. Mhm. So it's
Mhm.
basically you sort of decide. So, for example, one thing that will not be able to come into the set is, let's say, it also has three points, but they are connected not by straight line segments, but by curved line segments. And if they're connected by curved lines, yeah, something like that, then you cannot really call it a triangle. So you can say sort of it might have angles, but it doesn't. Uh, it isn't a triangle.
Mhm.
It isn't a triangle because, for example, if you apply, yeah, or like that, because essentially, if you let's say apply a Pythagoras here, it will not work, right?
Mhm.
Well, it is possible maybe that it will work in specific cases, but generally it would fail.
Mhm.
But also, for example, I had this consideration: a straight line, is straight line also a triangle? Because imagine, for example, you just draw a straight line, and let's say this line that you draw is a hypotenuse, right? And then we say one of the sides is 0, and another side is the same length as the hypotenuse.
Yeah, but
Uh,
like we already assuming that we have proper triangle in this set A, and using this set A, we want to show that the we want to show that like the this relation um
mhm. So
is
so far we
meeting
defined the
these
set.
three
So far
criteria.
we defined the criterion for deciding if A is an element of this set or not. But so
Mhm.
far we didn't define a relation, right? So far we only defined a criterion for deciding if an element is going to be part of the set or not. Mhm.
Mhm. So I think we don't have to, yeah. So we we can just assume we have a proper triangle in A, and then I think we can just take a Cartesian product.
Yep, yep.
Hmm.
And then we can check the property. So we say A tilde RA means a specific triangle from this set, chosen at random, but one specific element is equivalent to itself. So a triangle is equivalent to the same this triangle itself, right?
I mean, we can't use equivalence in this setting. We should use some relation, I think.
Oh, no. I am using the word equivalent because we are checking. Yeah. So basically, what I'm doing is when I use the word A is equivalent to A, I mean is that if it does work out to be an equivalence relation, then using the word equivalent between the two elements is the right way to call it, right? So once you have confirmed that all three properties are satisfied, then you can say an A is equivalent to A.
Yeah, we can call that relation is equivalence relation.
But what I mean is, before you checked, so let's say it doesn't work out to be an equivalence relation, then even though you said A is equivalent to A, it turned out to be false, that the equivalence relation did not hold. It basically broke down at some point because some property was not satisfied.
So you
But
want to assume that this relation is equivalence relation, and then whether find it actually works
yeah,
in.
it's basically, I think I'm sort of being a bit free with the terminology. So I'm saying I am reading the first line instead of A tilde RA. I say A is equivalent to A. But when I'm using the word equivalent at this stage, I am already assuming that it is an equivalence relation, which is kind of wrong. That's what I mean.
So your approach is first assuming that this relation is a equivalence relation, and
Equivalence
then whether
relation.
check this
Mhm.
three folds.
Because then in terms of a verbal expression it becomes easy. So for example, I can say if triangle is equivalent to exactly same triangle, yeah, it seems like it works out. If a triangle is equal to another triangle, then the other triangle is equal to the first triangle, which sort of also makes sense. And in the third case, I would say if triangle A is equal to triangle B and triangle B is equal to triangle C with respect to is equivalent, sorry. If triangle A is equivalent to triangle B, if triangle B is equivalent to triangle C, then triangle A is also equivalent to triangle C, sort of the way you would speak it. You see what I'm doing, right? It's basically I'm sort of already implying that it is an equivalence relation, but it's if it works out, then it should be fine.
Yeah, but what so something still not clicking for me
Mhm.
is so I feel like we have some if we like find some like real like examples like this, we need some statements that yeah comparable for our relation. Then if this
Let's
statement
say with respect to the triangles, the statement says that uh, it is a relation. They are two elements are in relation if they are both triangles. So basically, what type of triangles, what size of triangles doesn't really matter. As long as they're both triangles, they are related. Because you can have different classifications. Like, for example, I previously mentioned, we can say it's enough to say if they're both triangles, that then they are related by this relation. Or we can
okay.
say if they're right-angled triangles, then they are related. But if they are not right angles, then they are not related by this relation. And then we essentially have different types of equivalence. So one tries to say every triangle is equivalent to another triangle, and another one is saying that only right angled triangles are equivalent to right angled triangles and not equivalent to non-right angled triangles. Yeah.
So I think, as you said, we can construct relation A and B as A and B are triangle. So this just
Yep.
property as
Yeah. Yeah.
our relation. So
Hmm.
then we can check.
If those three criteria are satisfied.
Yes, right. A and A are triangle. Yeah.
Yeah, it seems to be satisfied immediately.
If A and B are
Hmm.
triangle, then B and A are triangle. Yeah. And if A, let's say just
I think
then
it's actually I think it's very important to put in the first case you don't need the if, but in the second and the third
yeah,
one
yeah.
you ifs. Yeah.
I will just use this implication, then it's
Yep.
automatically using B, C. So A and B are triangle and B or C are triangle, then
Yep.
but I think it feels a bit weird. I mean, it is too general that setting that A and B are saying this triangle because
But if I think you can think of it in the sense that when you say they're equivalent, you essentially compare a specific quality. If you're saying you're comparing whether they're triangles or not, then it's a general, very quite general property. If you are comparing if they're triangles with a side length of one and a right angle, and for example, one of the sides is bigger than the other side, then it's a more specific criterion, and then it would have less elements which would satisfy it, right? So you can either have a very general equivalence relation or a very specific one, and both are valid. Both are equivalence relations, but the criterion for equivalence is different.
Mhm. So I think it would be more beneficial that we use a specific case because if we use this setting, what I just write,
Hmm.
can you see the
Yeah, I see everything on the screen. It's visible to me.
I'm just moving the okay. So if we use this statement that I think it is like meaningless to think about equivalence relation because i- like A and B are triangle means A and B are just set of A, so we can just we don't even have to introduce relation or Cartesian products. We can just check whether A and B is elements of A or not.
But in this case again it's a general, but let's say we want to see if it is both are right angled triangles, then we would have a difference because A can be a right angled triangle and B is not necessarily a right angled triangle.
Mhm. Yeah, but I think the we need some different I think we need some different statement because anyway we are making a statement like A and B are this,
Hmm.
then we don't even have to think about the symmetry because A and B are something, then B and A are something. So
I'm thinking, imagine we're trying to make a proposition which would describe a relationship. Then we would say if both A and B are triangles, then they are equivalent. It's like a proposition you can make, right? So we define their whether they are equivalent based on the criterion if they are both triangles.
I feel like um the example we are making right now is a not good example for learning purpose, feel like
Mhm.
because
I was also maybe it's quick to switch. For example, let's say we're talking about digits, and let's say we're talking about, for example, digits from 0 to 9, so that we have only the first 10
Mhm,
digits.
mhm,
And let's say we want to see, for example, first digits 0 to 9 are written in the Arabic way, right? Like normal writing, 0, 1, 2, 3, 4, up like 9. Yep. And let's say we have another set, for example, which has the same digits but given as represented as Roman numerals.
mhm,
And our question is, can we give an equivalence relation between those two different representations? So even though visually they look different, but in terms of a relation, we can say that, for example, 0 does not have an equivalent in Roman numerals,
mhm,
but 1 is equivalent to this like big I in Roman numerals in
mhm.
terms of the meaning, but not the representation. But in terms of the meaning, it has the same value, right? So somehow can we put those two into a relationship? It's also like in this case we have set A of Arabic digits and set B of Roman sort of numerals. I'm not sure you can call them digits because they like are combined of symbols. Yeah. In this case, we actually do have two different sets,
Mhm.
but what we're trying to find out if they point to exactly same value, even though they have a different visual representation.
Mhm. I think we can construct, define
Mhm.
A and B.
Because I wrote down a definition specifically given by Professor Cho in YouTube video, and it said the following: an equivalence relation is the rule that decides which objects should be treated as the same.
Mhm. So, so in here we can, so first reflexivity, yeah, holds.
Yeah. Mhm.
But the problem is, if we take a different set as a Cartesian product, we can't.
It's not very clear what the reflexive would mean here. So even though, for example, one in Arabic and one in Roman way has the same value, but how can we compare if they're the same, right? Because reflexive, how can we compare this concept of reflexivity if they are coming from two different sets?
I mean, in non, even like non-homogeneous Cartesian product,
Mhm.
and can create a relation. That's what he said, right?
Non-homogeneous. I think basically his statement was the following: uh, in general, relation is not A cross B. But I think he said the word in general, which means that it's not impossible. It's just usually it's not. But in the example that I've given with the Roman and Arabic
Mhm.
numerals, I'm not exactly sure. So it seems like how do you actually check the first property?
Yeah.
So from a human perspective, it seems like can you show that one written as a Arabic and one written as Roman is the same value? And you can say, well, yeah, it makes sense. But how can you mathematically precisely show that A tilde R A is true or not?
I think we can even watch the video together because I also watched the video before we yesterday before we have a like pre-meeting. But
Mhm.
yeah, I think I didn't catch the details. I mean, now I think I can catch more details because we have discussed this twice. So I
Mhm.
mean, if you don't mind, I think we can watch the videos we like sharing here and then also discuss about the like lecture videos. Is it
Sure, yeah.
okay? Yeah, yeah.
But my question is, do we first maybe go through the material by ourselves? Like, sort of, do we go through the material first and then we watch the video because we will have more details to recognize in the video? Or do you want to watch the video sort of now and then come back to the material?
I want to so like the reason I want to I missed the expression that Professor Cho said non-homogeneous Cartesian product also could
Mhm.
produce a relation because
Yeah.
then
Okay.
like reflexivity does not make sense in
I,
this
I will
setting.
I will point out when I hear it in the YouTube video maybe. So shall we do it now so we don't
Yeah, yeah, yeah. I think I'll just stop sharing for a moment and then yeah. How can I stop sharing?
I haven't really been using that technically enough, so I'm not sure.
Oh yeah. Okay,
Mhm.
I will play it in a moment. Maybe we can also take the second hydration break.
Sure, yeah, yeah.
Mhm.
Yeah, for me, I realize if I speak for a while, somehow I get like coughs. So
Yeah, we are getting old, so
I think it's only for some reason in this type of weather. It's not happening all the time. Just
yeah. I mean it is actually really dry.
yeah,
So
yeah, probably because of that. Yeah.
I think yeah, I think I will play it in a minute.
Yeah, maybe while you're uploading the sort of loading the video, maybe I can send you by WhatsApp the message which I had about my screen overheating, about my phone. I think it might be interesting just to see how it looks like. Yeah, that one.
I mean, honestly, like I I watched the like video before we take a look at the notes, and it was quite a bit hard to check every detail. So
I think actually because you're going to be rewatching it after we already mentioned about specific
yeah.
nuances, it will actually be more open, revealing what exactly happened.
But for now, I really want to watch the video together and discuss about it because I was surprised at how much I missed from videos that while you um talking about
And maybe in case I misunderstood something, you will specifically point out that I misunderstood something while watching the video.
and I think there's no like um intellectual problem like because we are playing the video in our channel, so right? I think there's no problem with it, maybe.
Intellectual property rights, that stuff.
Yeah, I think it will be okay. So we have lecture three.
Yeah, my guess as well. Well, in the worst case, we will have to erase it from the video, but yeah.
Yeah. hmm Okay. So I think, can you see? Oh no, I'm not sharing right now. Mm, hello, Google Chrome.
Some screen is appearing.
Yeah, yeah. Um, Okay.
Yeah, I can see it now. Hmm.
Can you
And
also
then
Everyone,
like listening the audio from the video?
can you
on this
wait?
video, based on the third note of
Yeah,
from the
everything is
basic to graduate mathematics, we will explain relations, equivalence relations, equivalent classes, and partitions. In the previous two notes, we studied sets, functions, images, inverse images, one-to-one functions, inverse
I cannot hear the video now.
natural next step. A function
Okay, I will do the sharing again. I think maybe I can
It
um
basically switched off your microphone. I stopped hearing the video, so I think I heard the video because of your microphone.
okay, maybe background. Share sound. There is share sound optimized for video sharing. Show you Windows. Yeah, I think I can do it again. Just a moment.
Sure. Yeah.
I just found that there is a yeah, share sound optimization. Okay. It requires my
was a special kind of so-called a relation that assigned exactly one output to each input. This note, we begin with more general concept of so-called a relation. And then among other relations, we study a very special kind of relations called an equivalence relation, which groups objects into the same kind. These notes organized into few major stages. In the first stage, we look at function again as a special case of relation. A function connects elements of two sets by ordered pairs, but it satisfies the special condition that each input is connected to exactly one output. And in this another next stage, we define general relation. A relation is a way of recording which element is connected to which element between.
can you hear the audio now?
Yeah. Yeah.
Okay.
Basically,
Okay,
yeah.
okay.
You can also hear me, right? If I tell you where I hear a specific phrase, and if I
Mm.
understand it correctly, then I can stop ask you to stop the video, right?
Yeah, okay, okay. Now it's perfect then.
From the basic to graduate mathematics, we will explain relations, equivalence relations, equivalent classes, and partitions. In the previous two notes, we studied sets, functions, images, inverse images, one-to-one functions, inverse functions, and composition functions, and its characterization of one-to-oneness and onto-ness. The note today is the natural next step. A function was a special kind of so-called a relation that assigned exactly one output to each input. This note, we begin with more general concept of so-called a relation. And then among other relations, we study a very special kind of relations called an equivalence relation, which groups objects into the same kind. These notes organize into few major stages. In the first stage, we look at function again as a special case of relation. A function connects elements of two sets by ordered pairs, but it satisfies the special condition that each input is connected to exactly one output. And in this another next stage, we define general relation. A relation is a way of recording which element is connected to which element between two sets. Especially, we define an equivalent relation among relations in one set. An equivalence relation is a relation satisfying reflexivity, symmetry, and transitivity. In another stage, we study examples of equivalence relations. These include sharing same sets, grouping integers, and so on. And from there, we get the idea of defining the concept of the partition. A partition divides one set into several pieces that do not overlap while still covering the entire set. And in the final stage, we reached the key conclusion. Equivalence relations and partitions contain the same information. If we have an equivalence relation, its equivalent classes partition the set. Conversely, if we have a